Hello. Today we're going to be starting with the first chapter in Unit 1, which is 1.1, and it's change in tandem. Now, how am I going to explain this chapter? I'm going to explain it through solving the questions. We have a lot of questions going on, and trust me, by the end of this video, you'll understand everything related to this chapter. Now, at some questions, I may pause. I'll give you the formula. With others, I might just move on. I'll explain the question. I'll tell you what's going on. You'll understand the concept of this question, where you can solve similar questions in the future, hopefully. Starting with question number 1, a student starts to drive to school from home in a straight line and quickly realizes that they forgot their backpack. A student that's a sad student. Anyways, they're driving to school and, they're driving, right? And halfway there, they realize that they forgot their backpack. Now they're on their way back to home, right? Student stops the car and then drives back to their starting position at home. And what else? For this context, which of the following graphs could model the velocity v in miles per hour of the car as a function of time t in hours? Assume driving away from home involves positive velocity. So what is going on exactly? We have the student that is driving away from home, which is positive velocity. And then they're driving back home, which is negative, right? Driving away from home is positive velocity. Driving back home is negative velocity. That's what they mentioned, right? Because they mentioned away from home is positive, then you could just, not saying assume, you could basically conclude that driving back home is basically negative velocity. Now let's have a look at the graphs. We have the first one, which is driving away from home. They realize that they forgot their backpack. And what is going on? Well, what's going on is, I need to remove my cat. Okay, I'm back. So driving away from home is simply starting at 0. We have this point where they stop and realize that they forgot their backpack. Sorry, they don't stop at this point, they just realize that they forgot their backpack. And then they press the brake, right? Pressing the brake, they reach this point. Now they have a velocity of 0, and then they're basically going back home. This is when they have a sight of their home, and they press the brake, they reach home, that's it. So it is in fact option A. Why isn't it B? Because they start with driving away from home, which is a positive velocity, right? And not a negative one. So B is out. What about C? Well, C, they never went back home, right? They never went back to the starting position. And with D, we've mentioned that it starts with a positive velocity, not with a negative velocity. That's it. We can move on to question number 2. Now with this question, I'm going to explain what's going on before we solve the question. Let me pull out a whiteboard. Forget question number 2 for a second. Let's have a look at this graph. Let's say we have a graph that looks like this. Well, you need to understand what concavity means. Concavity means when we have a graph that has a concave shape, and the concavity may be facing downwards or it might be facing upwards. And it really helps you to tell whether a function, the rate of change is increasing or decreasing. And let me tell you what that means. In this case, the concavity is facing upwards, right? It's concave upwards. And the concavity with the second part is facing downwards. The concavity is downwards, correct? But what does this really mean? This does explain a lot regarding the rate of change. And always remember that when the concavity is facing upwards, the rate of change is increasing. When the concavity is facing downwards, the rate of change is simply what? Decreasing. It's that simple. Now, there are variations to concavity. Let me show you all the shapes so you don't get lost. Okay. We have this shape, right? Let's say we have a graph that looks like this. You see this? It does look decreasing though. Well, let me tell you this, that the rate of change is actually increasing. The rate of change, let me repeat that one more time, is increasing. Now you may ask me, what is rate of change? What does that mean, right? Let's take points on this graph. Let's take this point. Then let us take this point. You see this line? Y equals mx plus b. That's the equation of a straight line, right? This does have a slope of y equal to, let's say, negative 5x plus whatever, let's say minus 4. And you see this line? It also is a straight line, right? And it also has a slope. And guess what? The slope of this line is actually closer to 0, which might be like what? Negative x, negative 1 plus 4. I'm sorry, sorry. Let's say minus 7. Now, what is the rate of change for the first line? Rate of change basically means slope. What is the slope of the first line? Isn't it negative 5? What's the slope of the second line? Negative 1. As we're moving on to x, what is going on with the rate of change? Negative 1 to negative 5. Didn't this increase? Negative 1 to negative 5. Negative 5 is less than negative 1. So we increased from negative 5 to negative 1. Although the graph seems that it's decreasing, but as a matter of fact, the rate of change is increasing. Let me show you with this one. The concavity is downwards. Let's take this point. Well, guess what? This has, let's say, a slope of y equal to what? Well, it's very close to 0. We could say y equal, it's definitely not y equal to x. Well, you know what? Let's take this point. Just so you don't get lost. Let's say y equal to negative x plus 10. And then we take this point. You see this line? This is y equal to negative 10x plus 2, let's say. This is negative 10, and this is negative x, which is negative 1, right? Well, negative 1 is definitely greater than negative 10. So as we move on to the right side, when the concavity was downwards, this is simply what? Decreasing. So whenever the concavity is downwards, it's facing downwards, concavity downwards, remember that the rate of change will be decreasing. However, when the concavity is upwards, the rate of change is simply increasing. Now, let's try and solve. I do suggest you take the notes, okay? I'm not sure if the notes are clear though. If you want to go back through the video and take the notes at your own pace in a more neat manner, I would say, feel free to do so. I'm just gonna erase this really quick. I'm a bit slow, sorry about that. Okay, here we go. Have this left. This. There we go. Okay, the graph of the function f is shown. On which of the following intervals is the graph of f concave down? Well, concave down basically means the concavity is facing downwards. The concavity of this is facing upwards, right? So this would be facing downwards. This is facing upwards. Now, in this case, the concavity is facing downwards from negative infinity to negative 2, negative infinity to negative 2. Yes, that is true. The concavity is facing downwards. What about B? Negative infinity to negative 4 and 0 to infinity? Well, not really. From 0 to infinity, it's facing upwards, so B is out. Negative 2 to infinity. Well, from negative 2 to infinity, it's actually facing upwards. C is out. So what are we left with? We're left with D, which is negative 4 to 0. Well, negative 4 to 0, we'll have a look. From negative 4 to negative 2, it was facing downwards, but from negative 2 to 0, it's facing upwards. So I would say D is out as well. The answer is in fact option A. Now, let's go back to, yeah, that's it. But let me give you these variations in case you see them on the test. If you have a line that looks like this, concavity upwards, well, it's not a line, it's a polynomial, right? Or it's a curved line, basically. Or if you have a line that looks like this, concavity is upwards. Let's say it looks like this, concavity is downwards. And what else do we have? Yes, like this, like this. Yeah, it could also look like this. 1 second. This would have a concavity that's facing downwards. So yeah, that's pretty much it. Concavity that's facing downwards. So you have this variation, you have this one, and yeah, that's pretty much it. Okay, you can move on to the next question. So let's remind ourselves. Rate of change. Rate of change. It is decreasing when the concavity is facing downwards, 1 and 2. It is increasing when the concavity is facing upwards, 1 and 2. That's it. It's that simple. Let's have a look at this question. The rate of change of f on the interval of x is increasing from 0 to 1. They mentioned that. So what does this mean? This means that the concavity is upwards. When they mention the word positive and constant, the word constant means a straight line. You're dealing with a straight line. That's the first thing that should come to your mind. The word constant is a straight line. The word positive means that the slope is positive. Negative and constant, straight line. Negative means that the slope is negative, so you're dealing with a negative slope. This is a negative slope, and the rate of change is constant. So whenever you see the word constant, straight line, positive, positive slope, negative, negative slope. Increasing, decreasing means you're dealing with a curved line. Increasing means concave up, right? Or upwards, whatever you want to call it. Decreasing, concave down. Now the table describes rates of change of a function f for selected intervals of x. the function is defined for x between 0 and 4 and both of them are included, which of the following intervals is the graph of f concave down? Well, it's pretty straightforward, right? Decreasing means what? Concave down, and that is your answer. It's that simple. Okay, we're good. We can move on. Let's have a look at this question. A toy car travels around a circular track as shown in the figure. As the toy car travels around the track, its distance from the wall can be modeled by a graph where the y-axis represents the distance between the car and the wall and the x-axis represents the time. Which of the following graphs models this relationship as the car goes around the track 3 times without stopping? So this is the starting point, and this is the starting point, this is the starting point, and starting point. Now remember, the car is always coming back to the starting point, right? And what does y represent? Y represents the distance, where y-axis represents the distance between the car and the wall. So let's say the car is at this point of distance. Then you can tell that this is the furthest the car can be from the wall, right? But as it comes back to the starting point, it's basically back at 0 because it's touching the wall. And how many laps do I have? I have 3 laps. So 1, 2, and 3. 1, 2, and 3. Well, 1, 2, and 3, right? And do I ever have a negative distance? Well, not really, right? So we can cancel out B. So the car is basically doing 3 laps. 1, 2, and 3, correct? Now, what else do I have? The question is, which of the following graphs models this relationship as the car goes around the track 3 times without stopping? Well, it's always coming back to its starting point, which is this point. And it starts here, it does 1 lap, the second, and the third, right? So we can cancel out C as well, because it never comes back to the distance. It's as if the car is just going away from the wall. That's what C is mentioning. That's definitely not the case. What about A? Now we're down left to A and D, right? Why would you say A and why would you say D? Well, it's pretty clear that it's A, not D, because we're dealing with a circular shape in this case. It's not as if the car is moving in a straight line and then coming back, moving in a straight line and then coming back, moving in a straight line, then coming back, right? Instead, we're dealing with a curved line that basically represents what? A curved graph. And how else would I explain this? I would go about saying that if it's curved, then, well, yeah. Do we take this in pre-calc? I don't think so. Okay, well, yeah, you could just go about saying that since it's curved, then it's not really a straight line, that the car's, it doesn't have a straight path, right? And moving around a curved line will basically lead to a curved graph and not a straight distance, which is definitely not option D. D is a good second answer though. If you had have went with D, I would probably give you half a point. Like I would have just canceled the question out, but yeah, it is definitely option A. And yeah, that's pretty much it. Okay. Now let's move on to this one. The graph of the function f is given for -3 to 6. This is -3 and this is 6, right? Which of the following statements about the rate of change of f over the interval 2 to 6 is true? Okay, well, we're looking at 2 and we're looking at 6. They're mentioning that the rate of change is positive. What do you say? It's positive? Well, we're not sure though, right? Like, it could be positive though. And it could be negative. And the rate of change is negative. Well, it could be positive, right? But what we're sure of is that the rate of change is decreasing. Do you know why? Because this is simply concave down. That's it. And that is basically the answer. Always remember, concave down, decreasing, concave up, increasing. It's that simple. Let's move on to question number 6. The graph of the function f is shown over which of the following intervals is f increasing? Well, we just need to find where f is increasing. Like, as we move to the right, is it increasing, yes or no? -6 to -4, -6 to -4, it is definitely increasing, right? 2 to 5, well, it is definitely increasing, so yeah, that's it. Well, -6 to 0, not really. 2 to 5 it is, but -6 to 0 is not, so B's out. -4 to 2, -4 to 2, -4 to 2, it's not, it wasn't increasing at this point, right? So C is out. 0 to 2, it was decreasing actually, from 0 to 2. So this one's out as well. A is the correct answer. And yeah, that's pretty much it. Okay, now you need a calculator. You need Desmos as well. So a ball is thrown through an open window to the ground below. The height of the ball in meters at time t seconds after it is thrown can be modeled by the function h, given by h of t, which equals to the following. Which of the following describes the height of the ball above the ground? Well, the ball begins at its maximum height of 15.240 meters. The height of the ball decreases until it reaches the ground 1.82 seconds after it leaves the window. Is that correct? Well, you do need Desmos, and let me graph it on Desmos, and then I'm gonna graph it. So I'm assuming you're graphing this right now, right? I'm opening Desmos on my phone, and then I'm just gonna simply graph it. I'm gonna do my best sketch. So let's open a whiteboard. We have a whiteboard, and we have the question. Okay, there we go. What do we have? We have -4.9x squared plus 4.4x plus 15.24, right? Now after you graph it, what is the maximum point? Because I see the word maximum going on. Maximum, 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 maximum. Okay. So the maximum point, well, this is my best attempt. It's at 0.44898, right? Then we have 16.227. Now, The maximum point has an x value of 0.44 and a y value of 16.227. And what are they asking us for? Let's have a read of the first option. The ball begins at its maximum height of 15 point. No, that's not the case. It definitely does not. It's thrown through an open window, and the open window is at 15.24. That is correct. This is 15.24. It's thrown from this, right? If you graph it, when they tell you it's thrown from a certain height, it means that it doesn't start at 0. It doesn't start here. It actually starts at this height. So let's say this is a building and we're throwing the ball. Well, it started at a certain height, which was 15.24, right? And that's y. And it reaches its maximum point, which is at this point. And the question is, they're mentioning that it begins at its maximum height. No, that's not the maximum height. And let's look at option B. The ball begins at its maximum height, 15.24. That's also not the maximum height, so A and B are out. After leaving the window, the height of the ball increases to its maximum height, 16.228, which could be the answer. And the height of the ball decreases until it reaches the ground, 1.82. Let's have a look at... Okay, my phone glitched for a second. Okay, we're back. Okay, then they mentioned that the ball reaches the ground 1.820 seconds after reaching its maximum height. Well, that could be the answer, or it's option D. Well, what does D mention? Well, you see this is 2.2680, and after how many seconds, at what time does the ball reach its maximum height? It's when x equals to what number? 0.44898, right? This x, when x equals to 0.44898, y equals to 16.227. Now, after how many seconds the ball reaches its maximum height, it touches the ground? Well, if you do the math, 2.268 minus 0.448, what are we going to get? It's approximately equal to 1.820, right? Which is basically what C mentions. Then the height of the ball decreases until it reaches the ground, 1.82 seconds after reaching its maximum height, which is the correct answer. However, with D does look promising though. You mentioned that the height of the ball decreases until it reaches the ground 2.269 seconds after reaching its maximum height, which is not the case. It's not that 2 seconds after reaching the maximum height it reaches the ground. No. It's 2.268 seconds after being thrown it reaches the ground. Yes, that's correct. But if you want to find the time between reaching the maximum height and the ground, you subtract these two. And then the answer is 1.820. I hope that makes sense. Now, okay, let's erase all of this really quick. And let's solve the next question. I may split this video into 2 videos just for the sake of uploading it, because I don't want it to take forever. Now, question number 8. The table gives the characteristics of the rates of change of the function f on different intervals. Which of the following is true about f on the interval 3 to 4? It's positive and decreasing. The rate of change, whenever you see the word decreasing, what does that mean? Concave down or concave up? Decreasing means concave down, and that's it. So it looks like this, just in case you're wondering. This is positive, and it's decreasing, right? If you take any point, the rate of change will be positive, and it's decreasing. It's decreasing as we move with time. Like this would be y equal to, let's say 5x, and then this one equals y equal to x. Well, this is 1 and this is 5. 5 is definitely greater than 1. As we move on, it's decreasing. So f is definitely concave down and is decreasing. So f is decreasing and concave down. So it's option C. And I'm gonna pause the video right now. This is gonna be part 1. I'm gonna do part 2, which is the remaining part of change in tandem. I might actually split this video into 3. I truly don't know yet.